So in this video, I want to talk about what we call when we do transformations of linear regression equations. And in particular, what we're going to do is we're going to look at a data set, and we're going to start this process we call residual analysis. And we're going to go through and look at the residuals and the R-squared value to tell if a linear model is a good fit. And so I have this particular example here that says, it's talking about a planet that was recently discovered, or so they think it's a planet. And they're going to base it off of the 9 planets they already know. They're using the distance from the sun and the period of the revolution of around Earth years to actually determine if this is a particular planet. And this planet is called Eris. What I want to do is I want to go through regression analysis and try to predict whether this planet Eris is an actual planet. All right. Or if it's basically how many revolutions it's going to make in terms of Earth years. So here we go. The first thing we're going to do is we're going to graph this data, and we notice that when we graph the data here in the scatter plot, we can actually see that there is a slight curve in here. There is a slight curve in this data. And you can probably see it better if I draw this, but there's a slight curve. So because there's a slight curve already, I'm already thinking that a linear model may not be a good fit. All right. I'm already thinking that a linear model may not be a good fit. And that's because we see there's a curve in this pattern, or there's a curve in this data. So from there, I'm going to go and I'm going to look at the actual least squares regression. And here's the actual regression, and we can write it in terms of our variables. They tell us the dependent variable is the revolution, and the independent variable is distance. So we can write this, remember, using the context of the problem. So we can write it as revolution hat is equal to my intercept, negative 12.55, plus my slope, which is 6.11 or 6.12, and we'll say that's the distance, because that's the two variables of interest. Now, the other thing I'm going to look at is also going to be my R squared. And here my R squared I see is right here. And then R squared is approximately, R squared equals 0.978. So remember what this actual R squared value means. It tells us that 97.8% of the variation in the number of revolutions, or the period of revolution, can be explained by the linear relationship with the distance as measured by the astronomical units here. So that's what this actual R squared tells me. Remember, we have that sentence stem to help us interpret R squared. So just in case you may forget this, let me write it down real quick. We have 97.8% of the variation. Of the variation in revolutions, or the period of revolution is the actual variable if you look at the table. But 97.8% of the variation in revolutions can be explained by the linear relationship. The linear relationship with our x variable, which is distance. All right? So that's what that says. And now, so here we want to go and look at the actual residual plot next then. All right? And so I know what the scatter plot looks like, and I have an idea that because of that curve there, the residual plot is probably going to have a pattern in it. And when I go and look at the residual plot, which is what I have here next, the residual plot definitely has a pattern. It's a curved pattern. So right there, because of the pattern tells me that a linear model is not a good fit. Now, the R squared value we know is strong. It's very high. R squared is it's very close to 1. But because of this pattern here, because of that pattern, we're going to go ahead and try to do some re-expressions or transformations to try to see if we can knock out that pattern. And so recall when we do these transformations, then there are 3 different log models that we're going to use. There's the exponential model, the logarithmic model, and the power model. And they're all based upon how have you transformed the x or the y data points. And in general, what's going to happen is we can use either one of these models for instance, we use the exponential model when the y's are all greater than 0. So we have to make sure we check these particular things. Y has to be greater than 0. You can't have any negative logs. That's why you have to do this. So we're using the log or the natural log, ln here. And so because we're using ln as the log, when we go to solve these particular equations, we need to realize that our answer is going to be written in terms of logs. So we have to do other things to remove the log in the end. And we'll get to that in a second. But the first thing we need to know in our properties is that you can't have a negative natural log. So anytime you see the ln, that particular variable has to have all the values greater than 0 or be positive. So the next one, you get the natural log of x. That means that this time the x's have to be greater than equal to 0 or greater than 0. So for this one, the x's have to be greater than 0. And then for the last one, we get the natural log of x and y. So that means both x has to be greater than 0 and y has to be greater than 0 when we do this. And if we go back and look at our variables again, we'll see that all of the x's and all the y's are greater than 0. So we're good there. So now we're going to use the transformations. And I've given you the actual transformations with their r squareds. And we're going to write the equations out for each one because I want you to see those by hand. But if you look at the first one, which is the exponential model here, we can see that they give me the intercept and they give me the slope. And they tell me that the variable is natural log period of revolution, and the independent variable is distance. So I know my response and my explanatory variable. So I should be able to write an equation from that. Now the equation just looks like this. The dependent variable is the natural log hat of revolutions is equal to the intercept. And I like writing my intercept first when I write regression equations, but you can write the slope or the intercept first. It doesn't matter. But it's just 0.2, I'm only going to go 2 decimals, 0.28 plus 0.16 times your distance. So that's that equation. And I see that my r squared here is, the r squared for this particular graph is equal to 0.798. And if you look at this graph, you can see that there is still a pattern in the data. And so when we'll talk about that pattern, but there is a pattern in the data. And because of that pattern, we want to make sure that we keep that in mind when we go through this and realize that there is a pattern still. And notice that the r squared value actually got weaker. So this probably is not going to be a very good model to use here. So let's go to the next model and write the equation again. And this one we have, again, this time it tells us my variable dependent is revolutions, and the independent is natural log distance. So I've done the natural log on the x's. So when I write this, I'll write it like this. The sum is just revolution hat is equal to negative 2.11 plus 42.9 times the natural log of the distance. So that's that equation. And notice where the natural log moved to. The natural log is with the x. So when I wrote the slope this time, I'm writing with the natural log of that slope, because natural log is the slope times x. And here my r squared is 0.681. And again, if you look at this particular value here, if we look at this, we'll see that there is still a pattern sitting here. So again, probably not a very good model. And so in this last equation, when I write that one, it's called the power model, and I have natural log x and y. So when I write this, it'll be the natural log of the response variable, which is, this case, revolution again. So natural log revolution hat is equal to, look how far you have to carry this intercept, 0.000, I'll say 3, plus 1.5 times the natural log of your distance. So this one has the natural log in both the y and the x. And if you notice this, again, there's somewhat of a pattern still here, but it's more spread out, it's more scattered to an extent. But the big thing I want to focus on now is look at the r squared value. The R squared value here is now 0.999. It's basically almost 1. It's almost 100%. So even though there's still this pattern here, this model is still better than the previous two models, and it's also better than the original model because my R squared value is higher. So I'm going to actually go with this model here. And generally speaking, what I want to go with is I want to go with the model that doesn't have a pattern. But if there is a pattern, the next thing I want to look at, if I can't remove the pattern, next thing I want to look at is the R squared. Because R squared is the amount of variations being explained. So my chosen model that I want to use here is going to be the power model. And now what I have to do is I want to predict using that power model. And here's what I want to know. Which re-expression model is the best fit? We've already said that is going to be the model that goes like this. The natural log hat of revolutions are equal to 0.0003 plus 1.5 times the natural log of the distance. That's the first part. That's the actual model. Now, using that model, I want to predict the period of revolution for Eris, which is 102.15 astronomical units from the sun. So the distance is 102.15. So I'm going to go and plug in natural log revolutions hat is equal to 0.0003 plus 1.5 times the natural log of my distance, which was given to me as 102.15. So to calculate this, all I do is I work this part of the equation first. And so when I work this part of the equation, here's what I get. I get the natural log revolutions, the predicted natural log of the revolutions is equal to, I got 6.94. Now, if you go back and look at your data, that's not going to make any sense. And it's not going to make any sense because you're talking about the natural logs. We need to undo the log now to get it to the actual base that we wanted in. And to undo the natural log, we used its inverse base. And the inverse base of the natural log is e. So what I'm going to do now is I'm going to take this side of the equation and raise it to the e power. So I'm doing e to the natural log of the revolution. I'm doing that as a hat. It's equal to, if I do it to one side, do it to the other side in algebra, so that's e to the 6.94. And again, in your calculator, you have an e button. And anytime you press E, it automatically raises to a power. So I'm raising it to 6.94 power. And in the end, here's what I get. I get the revolutions are equal to 1,302.8 Earth years. And this answer should agree more with what we're actually working with now. Because if you go back and look at our table in previous, this one is considerably further. The distance from the sun is considerably further than any other distance that we've dealt with.